Hi, and this is Dr. Habib Ahmed, and today I will present the Silvaco TCAD simulation of perovskite solar cells. Here is the code, and here is the structure, and I will run the simulation once again, but I've already saved some of the results. In the structure, you can see over here at the top, we have indium tin oxide, then we have a layer of P-type nickel oxide, and then we have our perovskite material running from 0.15 to 0.35 micrometers. This layer basically is metal ammonium lead iodide. Then we have an N-type zinc oxide layer, and finally we have aluminum as the cathode contact. Before running the simulation and before talking about the code, let me give you a brief intro about perovskite solar cells. Generally, a solar cell is a device that directly converts the energy of light into electrical energy through the photovoltaic effect. Now, with the recent development of perovskite solar cells have developed more rapidly. Perovskite solar cells have the advantage that they have a longer diffusion length, large absorption coefficient, and low price. Perovskites have this kind of structure. They have an ABX kind of structure where A represents cation ions such as cesium and metal ammonium. B over here represents metal cation ions such as lead and tin, while X over here represents N ions such as chlorine, bromine, and iodine. So, perovskite solar cells are generally a hybrid of organic and inorganic layers, as you can see over here in the structure that I have simulated. This is an organic layer, while the nickel oxide and the zinc oxide are inorganic layers. Recently, perovskite solar cells have reported efficiencies up to approximately 30%. But despite its high power conversion efficiency, we cannot really make it totally organic because most of the electron transport layers and the hole transport layers in these fully organic perovskite solar cells remain sensitive to moisture. So a better idea is to use inorganic electron transport layer and hole transport layer suitable for these devices. So generally nickel oxide is chemically stable, inherently it's P-type, and it has excellent electron blocking properties. So nickel oxide is used as a hole transport layer. On the other hand, zinc oxide is used as an electron transport layer, and also zinc oxide inherently is N-type. Now, in this code, we are using a structure in which I initially have an indium tin oxide as the top contact, as the anode contact. Then we have the nickel oxide as hole transport layer. Then we have the metal ammonium lead iodide as the perovskite layer. Then we have zinc oxide as the electron transport layer, and finally we have aluminum as an anode contact. The work function of indium tin oxide is approximately, it's given in the code. Is it 4.5 or is it 5.5? It's 5.75 electron volts. While the work function of aluminum is around 4.6 electron volts. The band gaps of nickel oxide, metal ammonium lead iodide, and zinc oxide are 3.5 electron volts for nickel oxide. Generally it's in the range of 3.2 to 3.8, but we assume that it's 3.5 electron volts. A metal ammonium lead iodide has a band gap of 1.55 electron volts, while zinc oxide has a band gap of approximately 3.3 electron volts. And excuse me, we will run the simulation under AM 1.5 spectrum, which is 1000 watt per meter square, or you can say 100 milliwatt per centimeter square at room temperature and room pressure conditions. Now let us start talking about the code. Here is the code. For visibility reasons, I've copied the code to a Microsoft Word file. So I'm going to show you the code first in Microsoft Word document, and then we will run the simulation. So I start with Go Atlas. My structure is running from 0 to 1 micrometer in the X direction, as you can see over here. Along the Y direction, my structure is running from 0 to 0.5 micrometers, as you can see over here. Now, in order for comparison purpose, let me minimize this so that you can see both the code and also the structure. So my first layer is indium tin oxide running from 0 to 0.050 micrometers, or you can say it's a 50 nanometers layer. So I am defining a denser meshing at this interface, 0.050, and then the second layer is running from 0.050 to 0.150. So once again at this point, as you can see over here, I'm defining a denser meshing once again. Then the perovskite layer is running from 150 nanometers to 350 nanometers. So at this point, I will define the denser meshing once again. Then we have another interface at 450 nanometers, so I will define the denser meshing over here as well. And we can see the meshing as well over here. As you can see that the meshing is denser at the interfaces. Then over here I'm defining different layers. Once again, for comparison purpose, I'm moving it over here. Region number 1 is air at 0, 0. Then region number 2 is indium tin oxide running from 0 to 1 in the X direction and from 0 to 0.050 in the Y direction. Region number 3 is nickel oxide running from 0.050 to 0.150. So it's a 100 nanometers layer. Then region number 4 is metal ammonium lead iodide, and it's running from 0.150 to 0.350. As you can see over here in this structure, it's running from 150 nanometers to 350 nanometers. And metal ammonium lead iodide is not a user defined, it's not a built-in material in Silvaco TCAD, so I've set it as a user defined material, and I've already posted a detailed video on how to introduce a new material in the Atlas tool of Silvaco TCAD. So for more details you can look at that video. Then region number 5 is zinc oxide running from 0.350 to 0.350 to 0.450. Then I have defined the contacts as well. Indium tin oxide, which is a 50 nanometers layer, I've set it to anode, and aluminum, which is running from 450 nanometers to 500 nanometers, I've set it to cathode, as you can see over here in this structure. Then by using this command, I am saving the structure. Then we start another run of atlas by using the command of go atlas in order to find the short circuit current and the open circuit voltage. So I have saved the structure with this name, and then we run go atlas once again. Here I am actually importing that structure once again, and now we define the dopings for different regions. Region number 2 is indium tin oxide. Excuse me. And as we already know, excuse me, as we already know that indium tin oxide is a degenerately doped semiconductor material. So I've set its doping to 2 into 10 to the power of 20 per centimeter cube. For region number 3, which is nickel oxide, I've set a p-type doping of 5 into 10 to the power of 16 per centimeter cube. For region number 4, which is metal ammonium lead iodide, I've set the doping to a small value because this is our intrinsic layer. This is our photon absorbing layer. Similarly, for the zinc oxide, I've set the doping to 1 into 10 to the power of 16 per centimeter cube, and I've set it to n-type. Here I specify different parameters for these materials, like for example for ITO, I've set its band gap to 3.5. I've set different values for electron affinity, permittivity, density of states in the conduction band, and density of states in the valence band. Similarly, I've set its electron mobility and hole mobility as well. Now, this command over here actually identifies the name of a file from the SOPRA database. SOPRA database is actually introduced by a company called SOPRA. It is a thin film metrology company located in different countries worldwide, and these files actually contain the refractive index and the absorption coefficient information versus wavelength for different materials. For example, if you look at the Atlas user manual, you can easily find these the commands in order to call these SOPRA files. So for ITO, we are using ITO2.nk. N over here represents the refractive index, and K over here represents the absorption coefficient. Similarly, these are the electron and hole lifetimes for the indium tin oxide material. Similarly, we are introducing nickel oxide as well. Nickel oxide, once again, is a user-defined material, and I've set its band gap, electron affinity, and so many other parameters as well. Then we are introducing the parameters for metal ammonium lead iodide. Once again, it's a user-defined material. I've set different parameters for this. For example, the band gap of this material, which is a perovskite material, is 1.55 electron volts. Similarly, I've set the parameters for zinc oxide as well. And for aluminum, I'm calling the SOPRA file of aluminum.nk. Then for running the simulation, we are introducing different models. For example, bipolar, Fermi, Shockley, et al., field-dependent mobility, concentration-dependent mobility, Auger recombination. This is for band-to-band recombination in direct bandgap material, and this command is used for looking at the runtime output in Silvaco TCAD. Now, there are several methods, numerical methods, that can be used for calculating the solutions to semiconductor device problems. And basically, there are three types of solution techniques, which are Gummel, Newton, and Bloch. Now, the advantage of Gummel method is that it gives us a better initial guess. So it can be useful to start a solution with a few Gummel iterations to generate a better guess, and then Newton gives us a better quadratic convergence, but it takes more time. So after the initial guess is provided by the Gummel method, we can switch to the Newton method in order to find the complete solution. So that's why I'm using Gummel initially and then Newton. And this actually represents the number of iterations that our simulation should run before we give up on the convergence problems. This command is used for looking at different output parameters such as optical intensity, the bandgap information such as conduction energy levels, valence energy levels, and there are so many other different parameters. We can look at electron mobility, hole mobility, etc. as well. Now for the anode, which is basically the indium tin oxide, I've set the work function to 5.75. Similarly, for the cathode, which is aluminum, I've set the work function to 4.6 electron volts. Now we want to save the structure with these updated informations as well, and before that we provide an initial guess about the structure and then we plot the structure with this name. So this structure, as you can see, it has the same name as given over here. Now we want to look at the current voltage characteristics of the perovskite solar cell initially under dark conditions. So we over here we are running a sweep from 0 to 1.1 volts with a step of 0.01 volts. And we are saving the log file for under dark conditions with this name. Then we use log-off so that this log file does not interfere with the upcoming log files. Now here we want to introduce the AM 1.5 spectrum, which is the first step in the solar cell analysis, which is to illuminate the device. So we can turn on the illumination by assigning the beam intensity on a solve statement. So here we are actually talking about beam number 1 under AM 1.5, the standard test conditions at origin, so like slightly above the structure over here. And we are talking about AM 1.5 conditions, which corresponds to the standard test conditions, but in some cases we may encounter convergence difficulties. So we need to ramp up the beam, the light intensity, initially from this represents 1 watt per meter square to 10 watts per meter square to 100 watts per meter square to 1 kilowatt per meter square, which is the intensity requirement under standard test conditions. And after that, the next step is to extract the illuminated information. So now I'm creating a log file with this name, and then I'm running a sweep under light conditions from 0 to 1.1 with a step of 0.01, and then I overlay the dark, the IV curves under dark and light conditions. And I'm also saving the structure once again under light conditions in order to look at parameters such as the photogeneration rate and the photon absorption rate, etc. And then by using this block, I want to extract information. So here, initially, I'm calling this log file under light conditions, which we already saved by initiating this file. And then I use different formulas to extract information such as the short circuit current density and the open circuit voltage, the power curve. So I'm going to save it as I'm creating a power curve file with the name of p.dat. We can also determine the maximum power, the maximum voltage. You know, for fill factor, you need the maximum voltage and the maximum current, and the short circuit current and the open circuit voltage, and as the formula is given over here. And then we can also calculate the efficiency. Here I'm plotting the power curve, which we'll see later. Then I want to look at the spectral response of the solar cell as well. So I'm running another atlas command, and I'm actually here I am importing the structure which I previously saved. So if you look over here, I've saved the structure under light conditions. So I'm importing the same structure, and then I'm defining. Once again I'm defining the material parameters exactly the same that I did in the previous section. You know about the SO profiles. There is I noticed over here there is one crucial information. So right now I am at page number 7. Remember the page. There is one crucial information that is really important for the simulation of the perovskite solar cell, and that information is covered somewhere over here. I'm skimming through the code, so I almost forgot to mention that. So look over here. When I'm like we talked about the optical properties of different materials. For example, ITO, there is a SO profile in the Silvaco TCAD database, which has the optical properties information, the refractive indices, and the absorption coefficients information versus wavelengths. For nickel oxide, its properties are similar to zirconium oxide, so I'm calling that SO profile. But for our layer of interest, which is our active layer, which actually generates the electron and hole pairs, which is methyl ammonium lead iodide, it's a user-defined material. So we don't have SO profiles in the Silvaco TCAD database for methyl ammonium lead iodide. So then how do we include the optical properties of this perovskite layer? For that purpose, let us first look at the optical properties of methyl ammonium lead iodide. So I actually went to this website which has the information for the absorption coefficient and for the refractive index versus wavelength for look at the material over here. I've selected methyl ammonium lead iodide. So we have this information over here, and what I did is that in the same folder that I've saved the code, this is our code of interest, as you can see over here. I saved the NK file for methyl ammonium lead iodide. As you can see, this is .nk file. So here I actually have 11 entries into this file where I have a set of triplets where the first entry over here represents the wavelength, the second entry represents the refractive index, and the third entry represents the absorption coefficient. So I've registered these entries from 0.3 to 0.90 micrometers from the same information that I received over here. And what I'm doing inside the code is I'm calling this .nk file into my simulation, as you can see over here in this code. I'm using index.file command in order to import this .nk file for metal ammonium lead iodide. Similarly, we don't have the SOPRA file for zinc oxide as well, so I created another index file for zinc oxide, as you can see over here in this folder, and in the description you can see that this is a .nk file. So and then I went to the same website, and here I looked for zinc oxide, and from here I chose like 5 entries, should be enough in order to cover the information. The software actually interpolates the missing values versus wavelength for refractive index and for absorption coefficient. So as you can see, I've saved this as zinc oxide.nk. So I'm calling this file as well into my code. Now with that said, let us go to page number 7 once again, and we were around here and where we talked about the material properties and then models, and now I want to look at the spectral response. So once again I initiate a solution, I create a log file. I'm looking at beam number 1 at 1 kilowatt per meter square, and I want to look at the spectral response from 0.050 to 1 micrometers with a step of 5 nanometers. 0.005 micrometers is 5 nanometers. And then I would plot this spectral response. And then I want to look at internal quantum efficiency and external quantum efficiency as well. So I'm saving that information as well by using these equations, and then we will plot the internal and external quantum efficiency in the same figure. So now that we have already talked about the code in detail, I'm going to go to the deck build environment of Silvaco TCAD, and here I'm going to run the simulation. I'm going to close this now. We'll close these two as well. Oh, I opened so many files. But anyhow, here is the structure. We can also look at the meshing. Hit apply. As you can see that I have introduced denser meshing at the interfaces and sparser meshing in the middle regions. This structure is under thermal equilibrium. We can also look at the energy band diagram of the structure. So I go to tools, then cut line, then I draw a vertical cut line across the structure. You can see the doping levels over here on the right side. For the nickel oxide film, it's around 5 × 10⁻16. For the metal ammonium lead iodide layer, it's 10 to the power of 14, and then it's 1 into 10 to the power of 16 for the zinc oxide layer. Then I am more interested in looking at the energy band diagram of the structure. So we select EC of T, EV of T, electron quasi-Fermi level, and whole quasi-Fermi level. So here is the energy band diagram. On this side we have nickel oxide, which is also obvious from the fact that Fermi energy level is close to the valence band on this side. Then this layer is the perovskite layer, and on the right side we have zinc oxide layer. As you can see that the Fermi energy level is now close to the conduction band. This is the structure under light conditions. So here we can look at photogeneration rates and also at photon absorption rates. I go to photogeneration rate. As you can see that the photogeneration is higher in the metal ammonium lead iodide layer. Similarly, we can also look at the photon absorption rate. So as you can see once again there, the photon absorption is also higher in the metal ammonium lead iodide layer, which is our perovskite layer. We can also draw a cut line across the structure in order to have a better depiction about the photon absorption rate. So as you can see, it's high in the at this interface between the nickel oxide layer and the perovskite layer, and then it exponentially starts dropping. We can also look at the photogeneration rate. As you can see, the photogeneration rate is highest in the perovskite layer, and then there is also some sort of photogeneration in the zinc oxide film. So let me close the figure on the left side, and then we can see, like for example, I right click on this, go to display, in order to look at the energy band diagram of the structure under light conditions. So now as you can see that instead of having a uniform Fermi energy level, now we have quasi-Fermi energy levels inside the energy band diagram. Similarly, here are our IV characteristics under light and dark conditions. The red one represents the current voltage of the structure under dark conditions, and the green one is for light conditions. As you can see, it crosses the it has an intercept on the x-axis around 1 volt. Similarly, the open circuit, so this is the open circuit voltage. Similarly, the short circuit current is around here, which is given by the y-intercept. Similarly, we also have the power curve over here, and we see the peak power around 0.9 volts. We can also look at the spectral response of this structure. See, here is a spectral response. It's like in the range of approximately 0.1 to, you can say it's still high in this region, but you can say like up to 1 micrometer and even beyond. Then we can also look at the internal and external quantum efficiencies for the same structure. So you can see that the external quantum efficiency is the highest in the range of 0.4 to approximately 0.55 micrometers. Finally, we are interested in the figures of merit for the perovskite solar cell. So in order to look at parameters, for example, open circuit voltage and short circuit current, etc., like here is the code in order to extract that kind of information. We click on this icon, which gives us the output variable. So you can see like the short circuit current density in milliamps per centimeter square as well, the open circuit voltage, which is 1.04 volts, the power, the maximum voltage at the maximum power point, maximum current at the maximum power point. Our fill factor is 57.55. Our efficiency is 0.02. It's not great. We need to optimize the structure. Obviously, we need to play around with the layers. But the purpose of this video is to show you how to simulate the structure, and then you can play around with the structure in order to optimize the efficiency. Similarly, we can look at other parameters as well. So that's all about the Silvaco TCAD simulation of perovskite solar cell. I hope this video was informative for you, and keep watching my YouTube channel. We'll talk to you next time. Take care. Adios.